What is nuclear fusion?
Nuclear fusion is a process in which two atomic nuclei come together to form a single, more massive nucleus, releasing a large amount of energy in the process. This is the same process that powers the Sun and other stars, where hydrogen nuclei combine to form helium, releasing energy in the form of light and heat.
Is it the same as fission?
Nuclear fusion is a process distinct from nuclear fission, which powers current nuclear power stations. In the core of the nuclear reactor, radioactive elements like uranium or plutonium have large unstable atoms that split apart to produce small ones. As the atomic nuclei break apart, they release fast-moving particles. It is the energy of these particles that can be converted to heat and used to drive turbines, thus generating electricity. Fission occurs naturally in the Earth, where there is radioactive material, and provides much of the energy to keep the Earth's interior hot. It is the basis of all radioactive processes, including cancer therapy. Fusion, on the other hand, is virtually non-existent on Earth and is the basic energy source of the whole universe, powering the Sun and every other star. In each nuclear fusion reaction, two small nuclei fuse together to make a larger one. Just as with fission, a particle is released carrying away the surface energy. This effect was first studied by Ernest Rutherford and his team at Cambridge University at Cavendish Laboratory. Ordinary hydrogen has only one proton in its nucleus, but there are two of its isotopes: deuterium with one proton and one neutron, and tritium with one proton and two neutrons. If they can be forced together, they may fuse to produce helium, leaving one spare neutron to fly away. Inside stars, continuous fusion is sustained because of the tremendous temperatures and gravity that squeeze them together.
What you mean nuclear fusion does not exist on our Earth, so I can observe?
Curious girl, I see. Nuclear fusion is a process that naturally occurs in the core of stars, including our Sun. In the Sun's core, hydrogen nuclei, protons, undergo fusion reactions to form helium, releasing an immense amount of energy in the process. The high temperatures and pressures within stars are conducive to sustaining nuclear fusion reactions.
Well, the process sounds too simple. Why does it fail on Earth?
It sounds simple, as you thinking, but is challenging to replicate and sustain on Earth due to the extreme conditions required for its success. Several factors contribute to the difficulty of achieving controlled nuclear fusion: high temperatures and pressures. In the core of the Sun, temperatures reach millions of degrees Celsius, creating a plasma state where atoms are stripped of their electrons. Achieving and maintaining such high temperatures and pressures on Earth requires advanced technologies and materials. Confinement: the hot plasma generated during nuclear fusion must be confined long enough for the fusion reactions to occur. Achieving this confinement without the plasma touching the walls of the containment vessel is a significant challenge. Various magnetic and inertial confinement methods are being explored to address this issue. Magnetic confinement: techniques like magnetic confinement involve using strong magnetic fields to trap and stabilize the hot plasma. One example is the tokamak design, used in projects like ITER, which aims to confine and sustain a fusion reaction for an extended period. Inertial confinement. Inertial confinement techniques involve rapidly compressing a small pellet of fusion fuel using powerful lasers or other means. The compression generates the high temperatures and pressures required for fusion. Achieving precise and uniform compression is a complex engineering challenge. Energy: input versus output. One of the significant challenges is achieving a positive energy balance, where the energy produced by the fusion reactions exceeds the energy input required to initiate and maintain the reaction. Many experimental fusion devices have struggled to achieve this balance. Materials challenges. The extreme conditions in a fusion reactor subject materials to intense radiation and heat, leading to material degradation over time. Developing materials that can withstand these conditions is crucial for the long-term viability of fusion reactors. humans have been working on nuclear fusion for at least 100 years. While significant progress has been made in understanding plasma physics and achieving fusion reactions, a practical and sustained fusion reaction remains an ongoing challenge. Despite decades of research, the field is still in its experimental phase, with many technical hurdles to overcome before fusion can become a viable energy source. In terms of success, researchers have achieved several notable milestones, including by sustaining plasma at high temperatures, over 150 million degrees Celsius, achieving fusion reactions in experimental devices, e.g., tokamak laser-induced fusion, developing advanced materials and technologies to support fusion reactors. However, these achievements are still a long way from the goal of creating a commercial fusion power plant. The journey has been longer than anticipated, and it's estimated that we are still several decades away from realizing the dream of harnessing nuclear fusion for energy production. In 2022, researchers at Lawrence Livermore National Laboratory, LLNL in California, achieved a breakthrough in nuclear fusion, yielding more energy from a fusion reaction than the amount of energy put in one. The experiment used 22.05 megajoules of light energy to initiate the fusion reaction, producing around 3.15 megajoules of energy. While this achievement marks a significant step towards clean energy, it's still a relatively small amount of energy. To produce a practical amount of energy, significant advancements in technology and scaling up the experiment are necessary. Approximately 315 megajoules of energy could potentially boil about 1.22 liters of water under the given assumptions. Do not forget to like and subscribe for more videos.